Welcome to this platform. We are going to discuss numerical examples in electrostatics. And to remind you, electrostatics is the study of stationary charges. It has a lot of applications, but we are going to deal with numerical calculations. The first example is about Coulomb's law. And as we know, as we recall that Coulomb's law is gives the relationship between the force between charges, 2-point charges that are separated by distance. And we recall that Coulomb's law states that the force between two charges is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of the distance between them. So for this case, we shall come up with the formula as F between the two charges equal to K Q1 Q2 over the distance between them squared. Distance between them squared. K is a constant. You remember it. It is 9 times 10 to the power 9 Faraday per meter. And these charges might be negative or positive as they are given in the question, but we are going to take the magnitude of the charges in the calculation. So therefore, force in this case, in the question given, calculate the force of attraction between two charges of -3 microcoulomb and 6 microcoulomb, which are separated by a distance of 2 centimeters. Then we shall sketch the field lines between them. So in this case, the force, we have the formula already, is going to be K, which is 9 exponent 9 times the charge. The first one is 3 times 10 to the power -6. Remember, a micro is times 10 to the power -6. As we said, we take magnitudes. Then the next charge is 6 times 10 to the power -6 also, divided by the distance x, which is 2 centimeters, but has to be in meters. So that would be 2 times 10 to the power -2, that is squared. This is going to give us the force as equal to 405 newtons. If you use your calculator well, deal with the powers very well. The next part of the question says sketch the electric field lines between them. So we now go to the charges. We have a -3. So -3 is negative, and then we have also a +6. We know that according to the rules of drawing diagrams of electric field lines come from the positive charge into the negative. So the negative will receive and the positive will give. So field lines will be moving in this manner. And then we shall have more fields like this. Then we shall have fields like that. Okay. Example 2 says that charges P, Q, and R have coulombs of -1 nanocoulomb, +2 nanocoulomb, and +8 nanocoulomb respectively. They are placed at the vertices of an equilateral triangle of side 10 millimeters. Calculate the magnitude of the force exerted on the charge at P due to those charges at Q and R. So we have an equilateral triangle. You see here, equilateral meaning it has all sides equal. So each side is 10 millimeters as the question says. And then therefore it has all angles, interior angles are all equal to 60. So this is going to be 60 degrees, all of them 60 degrees. Now we recall from the previous example that the force of attraction between two charges is KQ1 Q2 over the distance between them squared. So we can see small explanations. The force that we want is the magnitude of force exerted on P due to those other charges. So it is P which is experiencing the charge. So if it is experiencing the force, so if it is experiencing a force, it will experience force due to R and due to Q. we are going to deal with these independently, as though the other charge is not existing. So we shall see that there is a force that P experiences due to R. Force that P experiences due to R. We have seen that P is -1 nanocoulomb, R is +2 nanocoulomb, and C is +8 nanocoulomb. Now we need to get the force. Using the formula, we shall deal with P and Q. We have the charges. We can get the force at P due to R as 0.00072 newtons. Please work it out. The formula is here. And now R is positive, P is negative. It means that the force between them is attractive. Remember, unlike charges do attract. So if it is attractive, according to the question, it is P which is to be attracted. So P is being attracted. If it is attracted by R, it means it is pulled upwards. Pulled upwards. So that's the direction for force on P due to R. Let's go ahead and also calculate the force on P. Force on P due to Q. Force on P due to Q. We are dealing with the charge at P and charge at Q. We have everything. Remember, again, the distance is given as 10 millimeters. The distance is 10 millimeters between the two. Distance between the two charges. This is an equilateral triangle. Please remember that according to the question. So when you feed in, you're going to get an answer as 0.00018 newtons. So the force between P and Q is equal to 0.00018 newtons. You can calculate that one out, and then we see that Q is positive, P is negative, the force between them is attractive, unlike charges do attract. So if it is attractive, according to the question, they are saying find the force exerted on P. So it is P which is feeding the force. So if P is feeding the force and it is attractive, it means the P is attracted towards Q. So if it is attracted towards Q, the force must be like that, towards Q. That's true. Then now that means we have all the forces, but we are lucky enough, the force, this one, let me label it. This is going to be F at P due to R, and then this one is F at P due to Q. So let's now see a diagram that contains where we can resolve the components, because we can't find the resultant force at P unless, because you can see that there is a force here inclined at an angle of 60 degrees. This is force on P due to R, and then we have another force on P due to Q. So FPQ is already horizontal, we shall not need to resolve it, but FPR is inclined at 60, so we shall have to resolve it. This is now a continuation. We can see that we have, in the previous part, we had this as point P, this as point R, this as point Q. Equilateral triangle, 60 degrees, this is 60 degrees, 60 degrees. We shall not write the rest, they are not helpful. The strange color on the diagram showing the vertical arrow and horizontal arrow is giving us the resolved components of the force on P due to R. Remember that we had F on P due to R, F on P due to R was going towards R, the force was attractive. Then we had also another force here, F on P due to Q, the force was attractive towards the right. Now the worry that we have is FPR is inclined at 60 degrees to the horizontal. We must resolve it. So if we resolve it, remember that this angle here is 30 degrees. If you want, you can resolve it upon the vertical or the horizontal. You get exactly the same answers. The horizontal component of FPR is going to be, since it's adjacent to the 60 degrees, it's going to be FPR cos 60 degrees. Then the vertical one is going to be FPR. It's going to be FPR sine 60 degrees, sine 60 degrees. So if that's the case, then we shall get F vertical, the resultant force at P in the vertical sense. If you look at the diagram with all forces resolved, we have only one vertical force, which is FPR, sine 60 degrees. Remember, we already have the FPR calculated, so when you substitute it in this formula and multiply with sine 60, you're going to get F vertical as 0.00062 newtons. We go ahead to find F horizontal, which implies the resultant horizontal force acting at P. In this case, we have two forces which are horizontal. We have FPR cos 60 going to the right, and we have FPQ going to the right also. So that means we shall add them because they are going to the same direction to the right, and they are positive according to the vector. So this is going to be FPR cos 60 added to FPQ. So we have the FPR multiplied with 60. We have also the FPQ. If you multiply or feed in, you get the horizontal force FH as 0.00054 newtons. Now we have the horizontal and vertical, and you know that they are always supposed to be perpendicular to each other. That means that the net force at P is going to be the resultant of the two, FH plus FV, but of course, Pythagoras theorem, they are squared. So FP is going to be, if you substitute in the two values that we have this one and this one, substitute in the formula, you're going to get the final answer as 0.00082 newtons. That's the final answer, representing the net force acting on P due to the charges placed at R and Q.